Chemistry chapter 22, reaction kinetics, theory video 1. Now we have learned about the rate of the reaction. So basically the rate of the reaction can be measured by the concentrations of the reactants decreasing, and then the products then the rate at which the products are increasing, etc. So these are some of the measurements that we can take to measure the rate of a reaction. Now when you take a single reaction, we have learned that the rate of a reaction can be increased by increasing the concentrations of the reactants, and then when temperatures increased or when a catalyst is added, we can increase the rate of the reaction. So these are some basic stuff that we have already learned. Now now in this chapter we are going to figure out how this rate of the reaction is increased by these things. So why is the reaction rate increased when we increase the concentration? So what effect does the temperature have? So like that we are going to figure out what they do, and also we will be learning in detail about catalysis. With that in mind, let's move to the rate of the reaction. So defining the rate of the reaction is actually we have given the job to an equation: change in concentration divided by time taken for the change. So this is in relation to the reactants or the products. So the change in concentration divided by time taken for the change. So the concentration is in moles per cubic decimeters. So then the time can be measured in seconds, minutes, or hours. Why do we have to consider hours? Because some reactions are not that fast. Some reactions are very quick. Then we might want to use moles per cubic decimeter per second. However, if the reaction is very slow, we might have to take it as mole per cubic decimeter per hour or days or whatever. So that is one thing that we need to understand. Then we in chapter 9 we understood that we drew a curve to show the rate of the reaction, and then at a particular point when we draw the rate against the time, then the products, the formation of the products against time, we realized that we could obtain the tangent, and we could calculate the tangent of the curve and figure out what the rate is. So that is another important factor that we have taken into consideration and should understand, should know. Write down a note for this. First of all, the rate of a reaction is increased when the concentration of the reactants are increased, temperature is increased, or when a catalyst is added. The rate of a reaction can be defined as the rate at which the concentration of a particular reactant is decreased, or the concentration of a product increased over a period of time. So write down the equation: rate of reaction equals change in concentration upon time taken for this change. Then underneath that, write units: mole per cubic decimeter per second for slow reactions, mole per cubic decimeter per hour. That is for slow reactions. Mole per cubic decimeter per second is for fast reactions. Yeah, so now that is what we have learned. Now let's move on to rate equations. The units of rate reaction would be mole per cubic decimeter per second. Then in chapter 9 you have learned about the isomerization of cyclopropane to propene. So cyclopropane turning into propene is something that you have learned. Then we can follow the progress of the this particular reaction by following through the decrease in concentration of cyclopropane or the increase in concentration of propene. So now in this table it shows the change of cyclopropane concentration, the reactant concentration at 500 degrees Celsius. So all of them were measured at the same temperature, because if there is a temperature difference, that would actually affect the rate of the reaction. So to figure out the rate of the reaction or how it is affected, we have taken the same concentrations. So here a cyclopropane mole per cubic decimeter, it is 1.50. Then the rate is 1 into 10 to the power minus 3. Then the rate upon cyclopropane concentration is 6.67 into 10 to the power minus 4. A certain value has been obtained. When the cyclopropane concentration is 1, the rate has been marked as 6.67 into 10 to the power minus 4. So it has reduced. So the rate upon the cyclopropane concentration per second is the same value. Then cyclopropane, when the concentration is 0.50, the rate has reduced further to 3.30 into 10 to the power minus 4. But the rate upon cyclopropane concentration has remained almost steady at 6.60 into 10 to the power minus 4. If you draw the graph of rate of reaction against concentration of cyclopropane, will give us that the rate is directly proportional to the concentration of cyclopropane. So if the concentration of the cyclopropane is doubled, the rate of the reaction will also double. If the concentration of cyclopropane falls by 1/3, the rate of the reaction falls by 1/3. That is something that you need to understand. So the rate of the reaction is proportional to the concentration of the reactant. So that means that the rate divided by the concentration is going to be a constant, as we show in this chart. In this chart, rate divided by the concentration was a constant. So that is a theoretical part that you need to understand. So then we can put this into an equation. Rate of reaction equals K into cyclopropane concentration. The proportionality constant K is going to be, because rate of the reaction is directly proportional to cyclopropane concentration, we can write it as rate of the reaction is equal to K into cyclopropane. K is the rate constant. This expression, rate of reaction equals K into cyclopropane concentration, is called rate equation for this particular reaction. This is only for this particular reaction. We write rate equations without writing the multiplication sign. So as a result, rate equals K into cyclopropane. And also you need to understand these rate equations can be only found using experimental data. They cannot be found by stoichiometric equations. So as a result, we can figure out how it is, how it can be taken into account. Now, if you take the first reaction, hydrogen joining with iodine to produce 2HI, rate equation is rate equals K into H2 concentration multiplied by I2 concentration. Then nitrogen monoxide plus carbon monoxide plus oxygen giving nitrogen dioxide and carbon dioxide. The rate of the reaction, the rate depends on nitrogen monoxide squared, KNO squared. Then 2H2, 2NO, 2H2O plus N2, that rate equation is rate KH2 concentration into NO squared. So these are all found by experimentation, right? Before we move on to the next part, let's write down a note. Rate equations and rate constant. When the rate of a certain reaction is considered, its progress can be measured by measuring the decrease in concentration of the reactant or the increase in concentration of the product. When these values are obtained and rate calculated, we will observe that the rate upon the concentration of the product or the reactant being considered would have a constant value. This constant value is known as rate constant. If it is represented in a graph, it would be a straight line. This can be written in an equation where rate of reaction equals K into the remaining part is going to change depending on the equation. But if it is for cyclopropane, K into concentration of cyclopropane, or something you will have to use. It could depend on several, the rate equation, how to develop the rate equation. So it might change from one equation to another. If you take the isomerization of cyclopropane to propene, please draw this equation, cyclopropane changing into cyclopropene, and after that write down the rate of the reaction would be K into concentration of cyclopropane and the overall expression rate of reaction equals K into cyclopropane is the rate equation. Below are some of the experimentally determined rate equations and write this table down. It would give you an idea as to how these things are developed. Now let's see how these have been analyzed. In the first one, the hydrogen iodine joining to produce hydrogen iodide, the rate of the reaction is proportional to both of the concentrations of hydrogen and iodine. However, in reaction 2, carbon monoxide and oxygen does not, even though they are in the stoichiometric equation, it does not affect the rate of the reaction. So it depends only on the nitrogen monoxide. So it is a square rule. That is also something that you need to remember. Similarly, in reactions 3 and 4, there is no relationship between the rate equation and the stoichiometry of the chemical equation. So that is the reason why this we said that it can only be found by experimentation. So we carry out a series of experiments using a single reaction to find out its rate equation or what affects the rate. Now, if you take the third reaction, that is hydrogen combining with nitrogen monoxide to produce water and nitrogen gas, we can carry out a series of experiments. First, what we do is we have to find how the concentration of hydrogen would affect the rate by change in the concentration of H2. So we maintain the nitrogen monoxide concentration a constant. So this, if we do this right, it will show us that the rate is going to be proportional to the concentration of hydrogen. So that is we double the concentration of hydrogen, the rate also doubles like that. Then if you change the nitrogen monoxide by varying nitrogen monoxide concentration while keeping the concentration of hydrogen a constant, that will show us the rate is proportional to the square of the concentration of NO. To the square of the concentration of NO. So when you combine these two, we get KH2 into NO squared. That is actually that is very important because the rate depends on either the rate would depend in a varying way to the chemicals that are taking part in the chemical reaction. This is very important because the rate equation for some reactions would include some of the chemicals that do not even take part in the chemical reaction, or that is not shown in the stoichiometric equation. Therefore, it is going to be important. Right. I suggest that you do question number 1. And if you have any questions, you can ask me if you don't understand anything. After doing the question, let's move on to the order of reaction. The order of a reaction means the representation or showing of how the concentration of a reactant affects the rate of a reaction. We say that the order of a reaction with respect to a reactant is going to be the power to which the concentration of that reactant is raised in the rate equation. So that is the power that we write at the top is what we try to figure out. Now when we take the rate equation involving only one reactant, the order is power of the concentration shown in the rate equation. So in the second equation here, we can see that nitrogen monoxide in the second equation here, rate is NO to the power 2. So that power is what we are trying to figure out. That is the order of the reaction. If you so the order is 2 with regards to NO in that particular reaction. So if you are to write, if you are to find the order of the reaction, what we need to do is we have to figure out we have to distinguish between the order to a particular reactant and the overall order of the reaction. They are different. Now, if you take the earlier example, hydrogen and nitrogen monoxide, so in that one, for hydrogen, the order is first order because it is 1, power is 1. Nitrogen monoxide, it is power is 2, therefore it is second order. The overall is the sum of these powers, that is going to be 1 plus 2, 3. So, if for a reaction A plus B into products, the rate can be written as, rate equation can be written as Ka to the power m, B to the power n. Then A and B are the concentrations of the reactants, M and N are the orders of the reactions. M can be 0, 1, 2 or 3, and it is going to be rarely higher. So when the value of m and n are going to be 0, because we know that any number to the power 0 is 1, therefore we can ignore it. Sometimes we have orders which are not going to be whole numbers. It could be a half number as well. But the most important thing that you need to remember is the overall order is going to be the sum of the powers that are there in it. So now if you take CH3CHO gas, CH4 gas, carbon monoxide, it has an overall order of 1.5. So the rate will depend on CH3CHO to the power 1.5. So if there are free radicals involved in a particular reaction, usually we get a fractional order of the reaction. So when you are giving the order, you have to specify to which chemical the order relates to. Sometimes it could be an individual element, sometimes it could be for the overall reaction. Write down order of reaction. Order of reaction shows how the concentration of a reactant affects the rate of reaction. That is, the power to which the concentration of that reactant is raised in the rate equation. For example, for the reaction, write this down please. Nitrogen monoxide gas plus carbon monoxide gas plus oxygen gas gives you NO2 gas plus carbon dioxide. The rate equation is rate equals K within square brackets NO squared. So as you can see, as you can see, write down, continue to write after writing the equation. Because the rate equation is KNO squared, the order is 2 with respect to NO. Then for this equation, rate equals KH2NO squared, that is the other equation there on the reaction number 3 of the chart. For hydrogen, it is first order, that is the rate is proportional to hydrogen concentration. For NO, it is second order. Rate is proportional to nitrogen monoxide concentration. For the entire reaction, for the overall reaction, the rate is third order, as we take the sum of the powers 1 plus 2 equals 3. Then write down the general equation. Rate of reaction equals K within brackets A to the power M B to the power N, B concentration to the power N. A and B within square brackets, they are the concentrations of the reactants. M and N are the orders of the reactions. M and N can be 0, 1, 2 or 3. Underneath that, right? If the reaction involves free radicals, it could have fractional orders as well. Example, CH3CHOG giving CH4G plus COG. Rate equals K within square brackets CH3CHO to the power 1.5. I hope it made sense. If it did not, please ask questions. If it did, please do question number 2 as well. Now we are moving on to units of K. So the units of K will vary according to the form of the rate equation. So now K is going to be concentration divided by units for the product of the concentration terms. Now rate constant must be worked out from the rate equation. So the K is going to be mole per cubic decimeter divided by units for the product of the concentration of the term. So that means you take this equation, you take the equation and then take the rate equation, and then you have to calculate based on based on the rate equation. I hope that makes sense as well. Write down units of K will vary according to the form of the rate equation. So the rate, by manipulating the rate equation, that is, you take this rate equation and make K the subject, then you will have to take these two concentrations into consideration. So H2 is mole per cubic decimeter multiplied by mole per cubic decimeter squared. So you have to divide mole per cubic, the rate will usually have a mole per cubic decimeter unit. So you divide that by whatever the other concentrations, then you will understand, you will get the units of K. So K equals mole per cubic decimeter upon units for the product of the concentration terms. I hope you understood. If you did not, please ask questions. Then you will understand it better. But before that, let's go through this. Before you try the questions, let's go through these worked examples. Then you will be able to understand it better. State the units of K for the following equation: H2 I2 A2 HI. So then we have to write down the rate equation, which is obtained experimentally and it should be given to you. Rate equals K into H2 I2. So then we rearrange the equation to make K the subject. Rate equals H2 concentration upon I2 concentration. So because both of them are not squared or anything, you have to multiply it by one another. Then 1 mole per cubic decimeter to 1 mole per, the rate is mole per cubic decimeter per second. So that to that gets cancelled out. So as a result, you will be left with mole per mole dm to the power 3 per second, or dm to the power 3 mole per mole per second. So then we positive index form is written first, and also you have to remember the per second part that is coming from the rate. Then a 2H2 2NO giving 2H2O plus N2 rate equation depends on H2 and NO2. Then again we do the same thing. In the first one we multiply the rate is mole per cubic decimeter per second. In the hydrogen it is here they have actually made a mistake here. As you can see, it is nitrogen monoxide is what affects the rate of the reaction. Here they have made a mistake, so please don't follow this. As you can see, let me do the correct calculation here. So it is going to be, the rate is going to be equal to, it is going to depend on, as you can see here, it is NO. NO to the power 2 is what defines the rate. So the rate is going to be, K is going to be rate over H2 concentration and NO concentration to the power 2, not NO2. Nitrogen dioxide is not involved in this. Now what you do is, now you need, you have to substitute the units. Now the top one is going to be mole per dm minus 3 per second divided by mole for hydrogen it is mole per cubic decimeter. For NO squared it is, now if I write it as mole per cubic decimeter, it has to be multiplied by 2. It is powered mole per cubic decimeter squared. So then you will be able to reach your answer. I hope that makes sense to you. You can cancel out this to this, so then you will get mole squared, but the final answer they have got it right. They have written the final answer correctly. Moles minus 2 dm to the power 6 per second is the final answer. That is correct. I hope that made sense. If it didn't, please let me know. Then I will explain it further. If you have any questions, please ask them. If you did not understand, please ask questions. If you did, please do the questions.